In our last chapter we have learnt about motion of an object. And most importantly force that causes the motion. Let us now see as what happens when an object is dropped from some height. Never go up, only falls towards Earth. We observe that Earth moves around Sun. And at the same time Moon revolve round Earth. Question is, what is that binds them move together? In fact, this binding is caused by some kind of forces acting on the planets and Moon. Newton was sitting under a tree. An apple fell on his head. The fall of the apple made Newton thinking. Why does the apple fall towards Earth? Why not attracted towards sky? He thought, if Earth attract apple, can it not attract the Moon? Is the force same in both cases? Newton thought, if an apple fall on Earth, why not Moon can fall on Earth? Moon seems to be falling at every point on its path around Earth. Had it not falling, must have gone straight as shown here. As such the process continues until one revolution. Newton thought there must be some force of attraction between them. Direction of this force is inward towards the center of Earth. He called it as centripetal force. Now the question arises, if Earth attract Moon, in reverse does Moon attract Earth? If yes, means there must be an equal and opposite outward force acting on Earth by Moon, called centrifugal force. Newton called forces between the masses as gravitational force. Later Newton gave a gravitational law. And now Newton gave us universal law of gravitation. That states, every object in the universe attracts every other object with a force which is proportional to the product of their masses and, inversely, proportional to the square of the distance between them. The force is along the line joining the centers of two objects. Let us consider two masses m and m, placed d distance apart. As per Newton's law as stated, force F directly proportional to mm and also F directly proportional to 1 upon d square. Combining the two, F directly proportional to mm upon d square, or F equals gmm upon d square, where g equals gravitational constant. We put g equals fd square upon mm for c unit of g equals nd square upon kilogram square. If we put m equals 1 unit and d equals 1 unit, f equals g1 guna 1 upon 1 square, implies that f equals g means g is also a force acting between two unit masses placed unit distance apart. Therefore, when we take two unit masses, placing them unit distance apart, g will acquire a uniform force of 1n throughout universe. That's why g is called a universal constant. Gravitation, in fact, I, binds us to the Earth, e, prove the motion of Moon round Earth, e, and also prove the motion of planets around the Sun. If high tides, disturbance in sea water are produced due to gravitational activity between the Moon and the Sun. We have described gravitational force between the two masses. Let us see what happened when one of the masses are on Earth. Then the force is called as gravity. Whenever a stone is dropped from a high raised building, it is being attracted towards Earth, is due to gravity. If the stone is not thrown but dropped, we say it a free fall. Let us have another example. A boy threw a stone up. After reaching a certain height it stops, comes under gravity of Earth, falls back towards Earth because of gravitational force only, is called a free fall. So whenever there is free fall towards Earth, there is rate of increment in velocity, means acceleration is produced, which is due to Earth's gravitational force, called acceleration due to gravity. It is denoted by g. The unit of g is the same as that of acceleration, that is, m upon s square. Now let us consider a body of mass m falling freely towards Earth. Earth applies a force F onto the body as shown. which by second law of motion is equal to mass into acceleration, g, that is F equals mg. But F equals gmm upon d square, therefore, mg equals gmm upon d square, hence g equals gm upon d varg, where g equals gravitational constant equals 6.67 × 10 to the power minus 31 Newton meters square upon kilogram square. M equals mass of Earth, d equals distance of body to the center of Earth. If the body is on Earth, then putting d equals r in the formula we get g equals gm upon r square. Putting the values of g, m and r, we get g equals 6.7 × 10 to the power minus 11 × 6 × 10 power 24 whole upon 6.4 × 10 to the power 6. Solving, we get g equals 9.8 meters per second square. Now what we see here is our own Earth. It rotate round this axis of rotation called a polar line. We know Earth is not a perfect sphere. It is elliptical in size and shape. Elliptical here means egg-like. This is called an equatorial line, which is always perpendicular to polar line. When Earth rotates, this radius at equatorial line is more than that of this polar radius. We know g is inversely proportional to distance square. This means larger is distance, smaller is g. So when we go down from poles towards equator, the value of g decreases. We can also see that the value of g also decreases when we go up or deep down the surface of Earth. Let us drop a piece of paper and a stone from the top of a tall building. What we see is that stone reaches the ground first and then piece of paper. But when we repeat the same experiment from inside of a room evacuated of air, both piece of paper and stone will reach the ground together. Reason: we have a piece of paper and a stone here. This area of contact with air is larger than this area of stone. Therefore, air resistance on piece of paper is more than that of stone here. This experiment gives us two results. First, inside the room both the piece of paper and stone are falling with the same acceleration. Secondly, objects falling are independent of their masses.